he brought to us so much in regards to especially helping us develop our beaver mimicry programming for students in the summertime, and really developed a lot of partnerships for us as he was working with Jefferson River Watershed as a drought coordinator, and then had worked with Great West Engineering as a GIS analyst. So he did that also while being here too. So he's a go-getter for sure. Evan currently works for the Montana DNRC Hydroscience section as a groundwater hydrologist, and he helps to administer new groundwater appropriations and conducts research to better inform resource management and planning efforts across the state. My favorite part of his introduction is that he enjoys everything from fishing, hiking, mountain biking, and cross-country skiing. So I think anything that ends in an ing, including drinking beers. After the webinar, he's going to go find the best IPA and Helena. So that's Evan. Welcome. And I'm so glad to have you with us today. And thank you for being part of our Learn Where You Live series.
Absolutely. Thank you, Raylan, for having me on today. Happy to be here to talk a little bit about my research and kind of an overview of what that beaver mimicry and low-tech stream restoration process is all about. I was kind of, deciding whether I just wanted to talk or if I wanted to share my screen and do a PowerPoint. So I might do a little bit of both. And then because there's so few of us, I think it's a great opportunity for questions. And if anyone has any background that they need from kind of the project, I'd be happy to share that. Certainly it's a good give and take here, this format. So I'll share. All right, can you guys see that? All right, so yeah, just a quick overview. I'd shared some information on the Google Drive link, and there was a video in there that kind of overviews the premise of low-tech stream restoration. In this case, this is an example of a beaver mimicry or a beaver dam analog site just south of Butte, Montana. And this is really a climate adaptation, climate resilience project. And working with the Watershed Restoration Coalition of the Upper Clark Fork, there were sites developed in 2016, 2017, and 2018. And what you're looking at here are historic beaver meadows that have dried up. And so through the absence of beaver, these once upland areas with ginormous ponds and wetland and riparian growth and kind of everything you can imagine in a very healthy ecosystem became degraded as the beavers either were trapped or hunted, predation by different animals. That's just a few of the reasons why they might not be in these regions anymore. And so restoration practitioners come in and they install these low-tech structures in the stream, site source materials. And so you're looking at conifer limbs, conifer posts, mud, pretty much anything you get your hands on in these areas and putting that in the stream. And so you can see here a picture on the left. I have an example of a structure, and it creates kind of this waterfall effect or this waterfall drop. And not only is it storing water right there where the structure is, but it's also what you can imagine is increasing the groundwater over on the side as well. So that was kind of one of our questions that we wanted to figure out was how do these low-tech structures increase both surface water flows, groundwater storage, and groundwater surface water interactions, among a handful of other things. And so, we being housed at Tech and working with CFWUP, we got to use a lot of neat tools that were at our disposal, including drone work, which is a picture here on the right. A drone had taken that on a survey that it had done. And then among other geophysical surveys as well. But that's kind of the premise of it. It's a climate adaptation as these streams, have been impacted by reduced snowpack, increased temperatures. We're looking for a way to slow down and attenuate that normal hydrograph you would see across pretty much all of Montana, where you see this peak flow in about April to May, and then a reduced to base flow as far as stream flow goes into the later summer months. And so that's another impact from these local structures. I show this figure here, and I described it in one of my short videos, but it's a good overview and a good schematic of just looking at a cross section through a stream and everything that's happening from evaporation to runoff from the surface, groundwater recharge, groundwater discharge back to the stream, looking at what happens when there's a high water table, what happens when there's a lower water table, or a wet versus a dry year, which is really, really important to consider when you're looking at data is well, did it rain more that year? Was there greater snowpack? And we can't just compare, a wet year and a dry year together. We have to, kind of consider them independent and use other factors like in the reach, you have a control where there hasn't been restoration. You have a treated site. How do these change over wet and dry years? And when we put in these structures, you increase surface water flow potentially. You increase certainly the depth of water. But overall, how do some of these factors of groundwater exchange, this hyporheic zone in between surface and groundwater, all the way down to bedrock, how does that impact and how does that change as a result of some of this restoration? So some considerations, the monitoring started in 2016 is one of the more important aspects of restoration. As you start these new projects and you're like, great, let's throw all this stuff in the stream. That's perfect. There can't be any side effects to that. It's like, well, you can say that, but you don't know unless you monitor it. So having a very well put together monitoring regime and a schedule, I think, was one of the most important things that we learned as a result of this project. And so, in these mesic environments, which is moderately wet, is what it's defined at for mesic, is, we're looking at anything from trout to vegetation height to water temperature to stream flow to groundwater level changes, that groundwater surface water interactions. So really, we can monitor almost anything. And on the right here, I have an example of a typical monitoring site where we have a staff gauge in the stream itself to monitor the change in height or the stage in stream. I take a stream flow here. We have groundwater levels that we measure near and far from the stream. All things to consider when we think about impact to these type of environments. I mentioned looking at wet and dry years. The water year just started over a few weeks ago. So happy new water year. I feel like I'm actually one of the few to say that to folks, and people just don't get it. And I'm like, well, October 1st, it's a restart. And so when we consider, how much precipitation from snowpack or rainfall we get, it's something to consider when we look at our data as well. When we look at our data, in addition to all of the actual results and what we collect out in the field, understanding what and where you're working in is also really important. So the type of soil you're in, whether you're in clays, sands, silts, gravels, how deep is the bedrock in different areas? What's the slope of the area you're working in? And then also, what are the typical flows? What's the typical discharge at one of these locations? Are we, down at on the Clark Fork River, or are we up in the Blacktail Creek watershed just south of Butte? And those are important things to consider when you look at pre and post restoration data. I also, watched a webinar. Utah State does a lot of this low-tech restoration work, and they're also another great resource. They have a few guidebooks, and they've been at this sort of research and this sort of data for a long time. And one of the things that they had mentioned is having research and monitoring that's scalable. Can you come up with differences that are, realistic, or are they reasonable for the site? Are they within your percent error for the monitoring equipment you're using? All things that are important to consider when you're collecting data like this. Here's a little drone video that we've taken. It's kind of fun, just flying through the site. So we have a control upstream, and you can see the stream right here as we're going through a couple of roads crossing, which can impact some of our results. But this is just an overview of some of the data that can be collected, and some of the neat tools that we would use to kind of describe our sites. There's geophysical data, drone work, veg surveys, topo surveys, kind of the whole bit, fish surveys, temperature data. All these things are interesting and can be collected at these sites. And I guess for students, it's letting them know, hey, like, all of this is important from impact of beavers and also restoration, as far as looking at what are the impacts from a keystone species, is including the beaver, and how does this ecosystem engineer impact some of these things, and we're kind of looking at it from a closer microscopic level in a lot of cases, as far as the gain or loss in stream flow between two different sites, which can be really close. But also, beavers, what they can do is generate, changes in flow from a lot bigger scale. And so it really is, a scalable type project that we think about. The research is obviously never ending. These are just a few examples of things to collect. And, I've included here a geophysical cross-section that we had taken with the field camp at Montana Tech. And that helps describe, obviously, the aquifer shape and the storage potential for groundwater, and how groundwater levels can change over time. So kind of an advanced way to look at a site, but also an interesting kind of approach to it. And we had started monitoring back in 2016, like I'd mentioned, and really when you put it all together, there's a lot of data that comes out of it. And I think that was one of the most surprising things I learned, was that how quickly data adds up and how much there is to process. And so when we talk about the drainages, and there's these shallow groundwater piezometers, which are a little different than wells, and in that they're only screened here at the bottom. So how you develop and how you set up your monitoring is also important for getting the proper data that you're looking for. A handful of surface water monitoring locations out there, looking at the changes in flow between the two. And then we established what were called flux stations, where we used naturally occurring temperatures at different depths in the sediment to help us understand, is water flowing upwards to the stream or down from the stream. And over here on the side, I have an example. Your people might be in the way, so you might have to move them off. But as I mentioned, with the temperature fluxes, you can understand gaining and losing reaches just by changes in temperature from, the stream or lake and nearby sediments below. So just a few different methods to understand, what a stream is doing at certain periods of time. This is actually the last of kind of just my overview presentation here, just a general view of our results and, what we found. And, overall, we do see an increase in groundwater storage as a result of some of these low-tech structures. We see a general gain of flow in the treatment sites and a loss of flow in the control sites. This figure shows just that. Is during high flow at the treatment site, you can see we have this aquifer storage, and we have this water flowing from the aquifer to the stream bed. In the control site, where there hasn't been restoration, we see this general groundwater recharge, often confused with one another, but that discharge-recharge relationship is really important when you talk about temperature in certain areas of the stream and also habitat, especially for trout. In the low flow at the treatment site, we see an overall groundwater recharge, especially during high years where we have a high water flow or an increased stage in the stream, where we have this pretty much not a need for groundwater discharge back to the stream, where there's enough water in the stream and we recharge that aquifer for potentially later in the year. In the control site, we also see a groundwater recharge. It's kind of a similar circumstance where later in the year, you can almost always assume that, well, the stream might be, it might maintain its level, but the nearby groundwater will drop. So just some things that we found and we considered as part of this. Other factors were, increased fish counts. There were increased fisheries in some of our local areas. Temperatures almost always increased. As you increase and you create these little ponds, increase the surface water area that the sun could come down and beat on some of these streams. So that was kind of an interesting tidbit that we found, was increased temperatures in almost all circumstances. Yeah, increased groundwater storage. Generally, an increased groundwater recharge at a lot of these sites were what we found. But yeah, I think that's kind kind of it. That's a quick overview of what we found and kind of the last 4 years worth of monitoring. I developed this, as Raylene had said, with my thesis research, and it was an arduous process for sure. Is going through everything from the data collection and improving our monitoring network, contacting landowners to make sure that they were okay with us going out on their properties to collect flows and do these surveys. The list kind of goes on, but I know that was fast, but I'd be happy to take any questions or answer some of those prompter questions you had sent.
Hi, this is Christine O'Shea.
Hi, Christine.
I see that Clint Festridge had a question. So Clint, if you want to just get on and maybe ask your question.
Gosh, I have a couple questions now. First off, I love the idea of using aerial drone footage as a monitoring tool. And in the Forest Service, at least on the Custer Gallatin, we just don't have the ability, either the equipment or the folks that are certified to run that equipment. And so I was wondering if USGS has folks that could do that work for us, or if there's private companies or who you would recommend reaching out to for those services.
Great question. I'm not sure if the USGS has it. We were lucky to be involved at Montana Tech and having that equipment available. Water and Environmental Technologies out of Butte had flown a few of our sites, and they are, could be a potential group to reach out to, and they have that at their availability. But I mean, you make a good point in not having all these tools available, and for us to create kind of a monitoring protocol that is a lot easier than taking drone footage. As far as like taking photo points, it's like, well, that's an easy way to monitor some successes without having drones. So, I guess there's options, but yeah, I think WET's the only group I know of.
Thank you. The second question I have is related to project effectiveness. I'm wondering if there's a greater bang for the buck in doing BDA work if you're in a losing reach, or if there's less potential for success if you're in a losing reach, and maybe there's greater potential to meet your objectives if it's a gaining reach.
Yeah, that's a great $1 million question. I think that it is, it's site dependent. It's always site dependent. And when you set up these sites, you sometimes don't know what your system's doing. And a lot of folks don't have the time to figure it out beforehand. It's kind of just like, okay, go in and restore. I can't say that having a gaining reach and, performing that restoration is, more or less, bang for your buck than a losing reach. But, I think for BDAs, as far as habitat, I think it's a slam dunk no matter what. And that water is going to go somewhere. And a lot of the time it goes in the aquifer and then it returns downstream. So even losing that certain location, you might be gaining downstream. And I think that's kind of an important thing to remember is like, unless it's, evapotranspired or, evaporated, the water is always there. It's, it's got to be coming downstream somewhere. So it's just something to consider.
Evan, that's great advice and a great point, and I'll definitely remember that.
Hi, we have another question in the chat from Jody, and she wants to know, what do you look for when choosing a place to test?
Yeah, that's a great question. And as far as testing, I think that a lot of these sites are set up based off the restoration potential. And we specifically in this watershed, in this study, we set up the restoration based off drying areas. So historically, you could look on Google Earth and see ponds that had been there. Now you can go out there today and not see the ponds. And so we're trying to bring that habitat back. And really, for testing or performing that monitoring, I would say that I encourage everybody to do some sort of monitoring on restoration. And a lot of it's required, especially for the high profile monitoring or high profile restoration work, as far as like stream bank restoration or removal of tailings or removal of sediment. That restoration or monitoring, has to occur. But for these sites, I mean, it's just the more the merrier. And I can't necessarily say, why we monitored more on one site versus another. A lot of it's just accessibility. How long does it take to drive there? It's those small things that are, kind of the reason and the driving point. But
I have a question. Can you talk more about like just numbers of beavers, before and compared to after monitoring over a couple of years? Like, what is the population with animals in the ecosystem? How has that changed, or what have you seen change over time?
Yeah, I'm not an ecologist. I'm not a biology expert by any means. And there are no beavers in any of these sites. There has been, I believe, 2 restoration locations in the Upper Clark Fork where we've put in these low-tech structures, and then beaver have actually returned and kind of taken over what we've given them as a jump start for habitat in providing those two necessary things, wood and water, that beaver need. A couple landowners, they're the ones and the best people to actually talk to because they are on their site all the time. And I know one had said that, oh yeah, the geese are really enjoying the pond, and the pond referring to the one that we had built for this particular landowner. So right now, as far as I know, it's a lot of just qualitative. And we see animals here and there, and there's not as much data as far as a quantitative increase in elk or deer or wolves moving through these areas. I think it's kind of something that needs to be improved on, and that's why monitoring is so important. But good question.
Thanks.
Hi, Evan. It looks like we have another question from the chat. Josh was wondering if you could expand on the formula for stream flow and how cubic CFS, so cubic feet per second, is calculated and measured.
Yeah, that's always a good question, and it's difficult to explain at times. So I mean, a CFS, if you're looking for an easy way to think about it, I think of a beach ball. So you think about an 18-inch beach ball, and it's how many beach balls are moving past one point over a period of time. And so, these sites, if I'm looking at this stream right here that I've have on the slide, that's anywhere from 3 to 5 CFS. So there's 3 to 5 beach balls moving through. But we'll take measurements along the stream with equipment that measures velocity. And by knowing the velocity at those points in time and knowing the distance across the stream and the depth at which you're measuring that velocity, you can create really a series of rectangles across the stream. And these rectangles will now have a velocity in each of them. So if you take a width times a depth, so that's a foot squared, let's say, and you multiply that by a velocity, a foot per second, then you have a cubic foot per second, ft to the third over 3, or over s, or over any time. So, generally that's how we do it with equipment. You can, do a float method where you send an orange or anything that's spherical down the stream and time how long it takes, and kind of get a good estimation of CFS. But really, it's a cross-sectional area method is what we call it. And I hope that answers the question. There's lots of great resources out there that can probably describe it better than I can. You got lots of questions here. Should I answer a few of these? Like turbidity a concern? Yeah, is turbidity a concern? So turbidity, clarity of water. In these cases, I feel like we have pretty clear and pretty clean water. We were working in a pristine environment. Because these structures do so well at capturing sediment, generally all those fines, will just be, I mean, they're either pushed through from the velocity of the structures and they settle out and then they move through during the next storm event. So, turbidity is natural. And I feel like if you have a high turbidity, it's not a huge issue for a long time.
Thank you so much, Evan, for joining us today and being with us. We're really excited to see, and we got to see some scientific discourse between two different scientists, which was an extra special treat. Thank you, Evan Norman. Thank you very much.
Thanks, Chris.
I'm going to introduce Clint Sestrich, and I introduced him last week. And so you know that he's from the Custer-Gallatin National Forest. He's with the U.S. Forest Service. And so I think that this second presentation or experience with him, not only does it model some discourse and asking questions of other professionals between the two of them, but it really shows the diversity of his job in what he's doing. And so, we have vast tracts of public land that are owned by us. And these scientists who are managing these lands, and whether he is looking at a beaver analog dam, or if he is looking at stream restoration in another way, or standing on a slope in the fires, and talking about what sort of effects those are. All of those are related to not only resiliency, but management as well. And so welcome, Clint. Thank you for joining us again. And we're excited to hear what you have for us today.
All right. Hi, everybody. Thanks for having me. Good to see you all again. Just thought I'd start off by giving you a quick overview of why it's important for managers to understand wildfire. And I'm probably telling you folks stuff you already know, but thought I would just stress it anyway. So as you probably know, wildfire is a natural disturbance on our landscapes. In fact, it really drives the terrestrial vegetation and the structuring of aquatic habitats across vast areas. And as a result of that, our vegetation and aquatic ecosystems have adapted or evolved with those disturbance events, and they're actually pretty resilient to wildfire disturbance. But what has changed is we are seeing the effects of climate change combined with, a century of wildfire suppression. And so those things combined have created a situation where we have increased frequency and severity of wildfire across our forested landscapes. And it's really important that we understand what the effects of those fires are on our aquatic ecosystems, especially since we have, things like invasive species present on our landscapes and in our streams that weren't present in the past or historically. And at the same time, we also have some social stressors, like a lot of urban interface or, human habitation in fire-prone areas that we definitely have to manage for and make sure that we're protecting. So there's a lot of complexity there, and it's important that we understand how wildfire may affect aquatic ecosystems so we can make good management decisions. So with that, I wanted to share some education materials that we typically use through the Watershed Warriors program and get your input on them. And have to start off by asking whether you've had a chance to review the PowerPoint presentation called "Would You Fish a Burned Stream?" Just give me the thumbs up if you've had a chance to review that yet. Okay, so I'm going to go ahead and go through the presentation, not in great detail, because there's an actual exercise that I want to go through with you to kind of be the focus that presentation will inform. So I'm going to go ahead and open up the presentation and share my screen.
So while he's getting this loaded up, I'll tell you a little bit about what's in the folder. He has a video of him standing on a slope in the from the Bridger Foothill fires, which is very place-based and current for students. And then there is this presentation that he's opening up as well, which is about would you fish a burned stream? And there are some annotations there with it too. And so it looks like he's ready to roll.
Okay. Now I think we're good to go.
Awesome.
I selected slideshow. Okay, can you see this? Effects of wildfire on aquatic ecosystems?
Yes.
Yay. All right. So I always start off by asking the students, would they fish a burned stream? Because, it's through fishing that many of us actually have developed a fascination with aquatic ecosystems. And it's something that I think many of us can relate to. Wildfire effects are grouped into direct effects, those that happen right during a fire or immediately after from the fire heating itself, or indirect effects that happen later from the fire or spatially removed from the fire. And both the direct and indirect effects can be physical and biological. So some of the physical ones include, removal of vegetation, both ground cover and forested canopy. You can have soil baking, which changes the physical properties of the soil. Stream temperature can increase. And also the chemistry of water can change due to leaching of ammonium and phosphorus from ash or smoke. Some of the biological changes that happen directly from the fire can be dead trees. You can have fish kills resulting from stream heating or from those chemical changes. And then also combustion of the organic or living matter in the soil and organisms. Here we have a photo of some brown trout that died from a fire in New Mexico several years ago. Many folks have also seen this photo that was taken in the Bitterroot during the 2000 fires, showing that, fire definitely affects terrestrial organisms as well. The indirect effects from fire are typically driven by rainstorms or precipitation events in the post-fire era, usually in the first 5 years after the fire until vegetation starts to stabilize slopes. And the magnitude of these indirect effects depend largely on burn severity, which we're going to get into, as well as the terrain slope or how steep the hill slopes are, and then the magnitude of the precipitation events. So in understanding burn severity, it's important to know that severity refers to the effects on the soil properties. At times, severity can be correlated with burn intensity or how hot the fire burned, but really it's the duration too, or the combination of the intensity of the fire and how long it burned that causes the effects of the soil. So low burn severity, you typically have less than 50% consumption of the soil litter layer. And typically there's some char and needles that are left intact, as you can see from this photo below. Moderate burn severity often has kind of a mix of, orange needles in the canopy, but that doesn't always equate to the severity in the soil. The severity in the soil is dependent on there being 80% consumption of the litter layer and duff. And there can be recognizable leaves or needle cast on the ground, but most of that organic matter is combusted. Then with high burn severity, there's typically little or no ground cover. It's less than 20% of the litter that's left. And oftentimes you can have hydrophobic soil or soil that actually repels water. The indirect effects, at least the short-term ones, are decreased water infiltration because you have this water repellent soil layer. You have water that's running over the surface and not soaking in. And this water can actually reach stream channels quicker than it would if it had to go through the ground. And that means you can have increased surface runoff. And this overland flow can cause increased erosion and potential for increased sediment delivery to stream channels. And this has some biological consequences because increased sediment levels can be detrimental, at least to some organisms like fish, eggs, and fry. They're dependent on clean, clear water coming up through gravel to oxygenate eggs. And if those spaces are packed with sediment, eggs or fry can suffocate. And the same is true for macroinvertebrates. If there's no clean surfaces on rocks for them to colonize and feed, then macroinvertebrate densities can go down too. And then in extreme cases, you can have debris flow events or mudslides that are generated from, intense rainstorms over these high severity hydrophobic soils. These are some pictures from the Bitterroot. These debris flows can really affect aquatic habitat. Large wood is really important in stream channels for providing cover for fish, as well as places where they can get out of the current. And they also scour the channel to provide a good spawning gravel. However, these debris flows can move all the wood out of channels at times and deposit an extreme amount of sediment that can actually totally fill the pools that fish need to not only overwinter in, but just spend time into forage where they don't have to spend a lot of energy. And overall, this means that there's reduced habitat complexity for fish, at least in the short term, from these debris flows. And if you can imagine a stream channel totally filling with mud, that can definitely cause complete fish kills. Another interesting effect of fire is that once the canopy is removed, you have more sunlight that's reaching the stream. So you have reduced stream shading. And this can increase stream temperatures, which can be bad for some aquatic organisms. But oftentimes, here in the Intermountain West, we have some very cold streams, and increasing stream temperature can actually increase the productivity because it makes streams actually more thermally suitable for fish. Not always the case, but that's oftentimes true. And with more light hitting the streams, you have more algae production or primary production, which feeds aquatic insects and in turn feeds fish. So you have oftentimes more or increased productivity following a wildfire. So here's a photo from a fire south of Livingston, and it looks pretty devastating, but I would argue that it really isn't, and we're going to go into why. So wildfires and debris flows are a vector that provide aquatic ecosystems with the building blocks of healthy complex habitat. Trees that burn from the fire eventually fall into stream channels and make great habitat. And then all of that sediment that's washed into those streams is eventually sorted by the wood and through some spring runoff events that create clean spawning gravel that's great for fish and great for colonization by macroinvertebrates. So it brings in the basic building blocks of good habitat. I'm gonna go really quickly through some data from my graduate work that examined the influence of the Bitterroot fires of 2000 on native and non-native fish, potentially, or I guess focusing on whether wildfire effects favored invasion of non-native brook trout. So the take-home message here is looking at these three streams as we see overall an increase in pools per mile over time, and also an increase in the number of large woody debris pieces per mile, both of which are good indicators of good habitat for fish. So over the long term, just to summarize, we have increased productivity, more large woody debris, increased spawning gravel, and clean cobble, which creates overall increased habitat complexity. Vegetation recovery from fire is highly variable depending on the severity of the burn. Here's a photo in the Bitterroot before and after a fire, and it shows by 2010, 10 years later, we don't have even small trees back, but the riparian vegetation has come back really well. In terms of fish population recovery, the speed of recovery is dependent on a variety of things. In the Bitterroot, with my study, we had streams that were connected to tributary streams where fish could recolonize burned streams or burned reaches. Here we have some data. We're going to focus on native West Slope cutthroat in red as they're the most abundant. And the fires happened in 2000, and then we had big debris flow events in 2001. And we see that for West Slope cutthroat in the post-fire, post-debris flow era, the number of West Slope cutthroat far exceeded the number pre-fire. And also we don't really see an increase in the number of non-native brook trout. And that relationship is the same for this stream, Chicken Creek, on the right. And for my grad work, we looked at 30 stream reaches, which were a mix of control, low severity, moderate, and high severity. Here are some streams without debris flows. And again, looking at West Slope Cutthroat, we see the numbers post-fire well exceeded the numbers pre-fire. And I expect that we're seeing that productivity effect on these streams and fish population. Here's some data from south of Livingston in this Anderson Creek drainage, which I showed you the picture of earlier. And essentially we've seen that the number of Yellowstone cutthroat doubled in the post-fire era from before the fires. Recovery, or the rate of recovery, again, depends on soil severity, burn severity, depends on how stable these stream channels are and for how long. So for example, if you have a drainage that doesn't have very good vegetative recovery for, let's say, 5 years, and you have a big storm event 5 years out, you can have channels that fill with sediment again. We're actually seeing that in 6 Mile Creek south of Livingston. So the clock can kind of keep getting reset for recovery. Also, as far as fish population recovery goes, if you just lost, a small proportion of the population, they'll recover pretty quickly. But if you lost the entire population, it might take longer. But it also depends on whether there's a source population of fish that survive the disturbance event. And that's referred to as a refugium or refugia. And that can be a tributary stream that didn't burn, or even a reach within a stream that didn't burn where fish were able to seek refuge. So I always end with this slide here showing some wonderful fishing in a burn stream south of Livingston. So that provides you general background, and sorry to rush through it, but if we have time, I'd like to go through the fire table exercise with you.
Yeah, please do. And while you're opening that up, we can do some questions.
Okay. Yeah, go ahead, shoot some questions while I open this.
There's a question from Amy. Is this a natural recovery of fish, or were some of them restocked into the streams? You might have answered that partially.
This is all natural recovery. And in Montana, we have, I don't know if it's a law, it's a policy that we rely on natural reproduction in our streams to sustain our fisheries. So that's pretty unique in Montana.
So Clint, it looks like you would, from what your research is showing, that we're seeing an increase of native fish and a decrease of non-native fish. Is that what I'm understanding, or?
Yeah, so we found that overall, the non-natives tolerated the fire not nearly as well as the native fish, which appear to be, well adapted to fire effects. However, there were a few situations where it wasn't the case. We saw one stream where brook trout really took off. And one thing that folks are noticing across the West is with climate change, we're actually seeing an increase in brown trout, which are tolerant to warmer temperatures than our native fish. There may be situations where, non-natives may be favored, but in my work, overall, the native fish were better adapted. Okay. So can you guys see understanding effects of wildfire on aquatic ecosystems?
Good to go.
All right. So understanding effects of wildfire. So we developed a table or model several years ago. I'm on a timer that's going through these slides. I don't know why it's doing this, but we developed a table several years ago. And this is something that you could actually build and incorporate in your own classrooms. And so what you need is some potting soil, some burn soil from a fire, some tree branches, both live and dead. And you can also use some model fish. I think these are like Schlei fish. They're toy fish. They provide a good visual aid, and then a watering can. And then here's a picture of our stream table, which is just melamine that's glued together. And then we have trays to place burned and unburned soil in so we can test a variety of hypotheses. So an overview of the model or the situation is that you have two watersheds. You have a burned watershed and an unburned watershed. Each of these watersheds drains into a first order stream. Are you guys all familiar with stream order? If not, it's just a way to describe the size of a stream based on the number of tributaries that there are. So first order streams don't have any tributaries. So we have two first order streams draining these watersheds. The two first orders come together and form a second order. Then the second order runs into a third order. And if the third order might be analogous to like one of our rivers, like maybe, the Yellowstone or maybe the West Fork Bitterroot. Here's a picture of the pre-fire condition. And this is a situation where you could just ask the students to describe what they see in terms of the vegetation, the soil, the number of fish in the stream before the fire, which is referred to by biologists as the carrying capacity. So how many fish will a stream support? The scenario is this. So you have a lightning strike in the lower watershed. You have strong upslope winds that push the fire along the east side of the stream into the upper watershed. You have a high intensity fire, the duration of which is pretty long, and it results in high severity effects to the soil. In the first year post-fire, you have a few high intensity rainstorms. Let's talk about the direct effects that we might visualize from our model. I would ask the students to think about if we had a rainstorm over this unburned drainage and the unburned drainage, what the effects would be. And we also use the table to talk about stream shading, which is one of those direct effects from the fire itself for loss of the vegetation. So some other effects you might see are dead fish, like the one here at the top of the screen in the burned tributary. You don't see many of them dying, but just in that tributary. Indirect effects are those after the fire. We're gonna look at some, or hypothesize about what might happen between our burned and unburned watershed. We're gonna have a rainstorm over our unburned watershed, and I always ask the students what they expect to see. Okay, so now we're gonna look at the burned watershed. next we talk about or hypothesize what the overall effects will be to our fish populations and habitat over the long and short term. Spawning fish. So we can end with the discussion on what we actually saw and whether our predictions or hypotheses about what we'd see in the stream table lined up with what we actually saw. And I just think it's a great interactive tool to have with the students, and you'd be amazed at the questions, the intelligent questions that we get when we do this exercise.
Clint, thank you for sharing that. That was awesome. I saw a lot of foreheads because they were coming really close to the screen and looking, which was pretty joyful. You guys, it's 5:03. We're going to take some questions for Clint and what you saw. I think that that's really important to honor that. And then if you want to stick around after for a conversation or a breakout group, you can do that. Otherwise, we're going to call it as is. You know, I think that this connection with our scientists is the most important thing right now. And so, questions.
Clint, I have a quick question about the hydrophobic nature of the burned soil. So what is it that causes the soil after a fire to change chemically like that?
So it's the loss of the organic matter. But in terms of what's happening at the atomic level with chemical bonds, I don't know. That's maybe an Evan question. Sorry to punt, Evan.
Yeah, I might just have to kick it back to you. I don't have a great answer to that. I think you nailed it with the loss of organic matter. It's about.
Thanks.
So having the debris essentially within the soil causes it to absorb more water.
Yeah, I like to think of the organic matter as a sponge. It really helps soak up the water. And it's interesting. We had some soil from the Bridger Foothills fire that we ran water through, and it was moderate severity, and saw that there was a little bit of water repellency, but also soaked up a little bit. So you could actually see, how that amount of organic matter influenced it.
So I guess I get another question for you. Why do you think this is important information for people to understand in Montana?
Yeah, so as I said earlier, I believe wildfire is super important on making sure that we have healthy aquatic ecosystems. It's human nature to be afraid of fire. We have 100 years that shows that our fear of fire has driven our policy in suppressing fires. But, if we don't maintain some fire on the landscape, we're going to lose a lot of diversity, I think, in terms of our aquatic ecosystems and the aquatic critters that are present and have adapted with fire.
I have a question. So I'm thinking that all this research from both of you actually is going to impact how we manage our forests in the future, that we've learned from our mistakes I know in the past when I did this forest in every classroom class, and they talked about how years ago they didn't harvest very much, and that caused a lot more fires. That was one of the reasons. But how is this going to change things for the future, this data?
No, that's a really good question. I think in terms of what's tangible on the ground, at the ground level, for me, it's biologists like myself working together with wildlife managers or wildfire managers to take advantage of opportunities to use fire to play its natural role where we can. Can't always do that when life or property are involved, but I think that's one way that can happen. And the other way I think is just for folks in upper level positions just being more informed so they can help influence policy. But in terms of forest management and timber harvest, economics drive a lot of what we do on the ground. There's a lot of timber harvest that we could do, but it just isn't economically feasible due to can't use helicopter right now or other tools because they're too expensive.
I guess I was thinking, with this Bridger fire and how they manage it. And I know houses, property is a big thing as far as fighting fires, but is a tendency now to let fire burn, like in Yellowstone. I know I see that practice to just, as long as property isn't in the way, that's, humans are always part of the problem, but are they looking to let fire take its natural course when possible compared to previously?
Exactly. So our forest plan or the document that directs how we proceed with fire, it does allow us to use wildfire on the landscape. And there's a decision support system called WFDS, or Wildfire Decision Support System, that managers go through right when they have a fire start to determine how they manage the fire and whether it could be used for ecosystem benefit. And it depends on, of course, the values at risk. What are the fuel conditions out there? What's the weather looking like? Just all those various concerns. But we definitely look at that option to see if it's possible.
Thanks.
So I have to ask you guys a question. Do you see yourselves using a table like this in your classrooms? Would you see this being a good visual aid or something that you would try to use yourselves? Cool. I would be happy to share information with you on how I built it, or maybe you guys have some far better ideas on how to build one that I would be interested in too.
We also have a question from Amy. Have you worked much with our tribal environmental programs in Montana or with is it Kuruk tribes? Can you say that, Amy? Because I know that I probably didn't pronounce that correctly.
It's the Karuk and Yaruk tribes in Northern California and Southern Oregon.
So unfortunately, I'm not familiar with those tribes, but in my neck of the woods, we do work pretty closely with the Crow tribe at times because this is their ancestral grounds. And we've worked with them very closely on some native Yellowstone cutthroat trout restoration projects, where we've actually had tribal members out removing non-native fish with us. And we also work very closely with the U.S. Fish and Wildlife Service, who has authority for managing fish populations on tribal lands. And so we work with them really closely on projects. For example, we're pursuing putting in some fish passage culverts on the reservation on Sage Creek right now, just downstream of the forest boundary, that would definitely benefit the national forest, as well as habitat on tribal lands.
Thank you. Yeah, just the curiosity with that is with a lot of the traditional ecological knowledge and with a lot of the traditional practices with not fire suppression, but using fire as a way to manage the land, just kind of looking at those as we're kind of learning from each other how those practices that have been happening for hundreds of years, going back to that way or allowing that way could help with ecological success in so many different areas.
I think it's a wonderful thought and a wonderful thing to pursue. And I'm not sure, I don't really know anything about how the Crow tribe manages wildfires, but I would expect they're using some of those traditional means, and I would definitely love to learn more about it.
Yes, and thanks Chris and Bill for putting in some information and links in there as well for the fire in the land and for the Piikani perspective as well.
Well, I would just like to say thank you all. You guys have the most important jobs in the world, and I really appreciate what you do.
Thank you so much for coming and helping us with this endeavor and bringing all of these people together and students, and it's important work. And so your important work is going to to meet our important work. And I can't think of anything more profound. So thank you for this. All of this stuff that he has shared is in those folders. The links to the videos and the IEFA resource Fire on the Land is in your standards documents underneath this module. You have access to all of this, and Michelle graciously opened up until February that you can implement any of these things in your classroom, as long as you are completing those first 2 slides with the attendance and the 3 dimensions of science education. And so those are those 2 slides that would need to be completed. Michelle, can you think of anything else missed?
No, I think that would be those 2 slides by the end of October. And then, for implementation and post pictures of it being used in your class or student work would be at the end of February, if that works.
Yeah.
It's really great, because if there's some way I can share that out, maybe we can get more people using this and get more place-based learning. That would be wonderful. So are we skipping breakout rooms today? Everybody for that?
Yes. We had an awesome meeting. I feel great.
Well, thank you guys for giving me the time. I appreciate your patience with the technology and my abilities to run it or not run it.
We understand. We're all Zooming with students and trying to figure that out. We definitely understand. So thank you all.
Thank you so much.
Right.
Thanks, everyone.